Okay. So here we go. Wrong place. Let me find. Okay, so it's gonna be over here. It's gonna be, what's it called? What unit is this? Unit 7. Momentum. Close all these. Okay, so unit 7 momentum. Momentum. Okay, so figure out a learning rate. So choose a learning rate. So you remember what the range for learning rates are? Like what's the lowest value for a learning rate and what's the highest value? Or do you know like the maximum value a learning rate can be? Okay, so epsilon. Okay, so epsilon, so let me go back to where we went to epsilon. So epsilon is to figure out, so epsilon is a tiny value because we need to find bounds for we need to get an interval to calculate the slope. So that's what epsilon is. So that's for how we calculate the derivative. But then the learning rate is gonna be, so the learning rate, it's to control how much. So because we get the partial derivative, but then you need to figure out like how much to use. Because if you use only the partial derivative, you remember from last time, you're gonna update way too much. So we need to take a fraction of the partial derivative. Okay. I forgot. Okay, so learning rate is different. So epsilon is to figure out. So epsilon is to figure out the interval to calculate slope or derivative. Okay, let me just make this clear for you. And then learning rate is the fraction. What do you mean apply? Like use it to determine the learning rate? Yeah, okay, so learning rate is different because since you're calculating the slope slash derivative for epsilon, learning rate, you're trying to figure out the fraction of the slope or derivative to update your parameters. Yeah, epsilon is really small. It's like 1 times 10 to the like -4 or -7. Yeah. Okay, so since if you don't use learning rate, if you update with only like this, yeah, okay, I need to go back to learning rate. Okay, so so without learning rate, I'm gonna just go back here. Okay, so without learning rate, what happens is that you're technically over here, if you have a learning rate, then you're technically having 1 multiplied by the negative of the gradient. I mean, the negative of the derivative. So technically your learning rate is already 1 if you don't set a learning rate. And then so what you get is that your you increase your weights and biases too much because your bias should be 20 and your weight should be 10. But then you increase them way too much from their starting values that your cost just explodes. So what you need to do is set a learning rate less than 1. So what's your next guess? Okay, that's reasonable. Let me. Okay, so what we have is a learning rate of 0.4 and the coefficient of friction is going to be 0.5. So what we do is, okay, oh, uh, okay, so learning rate, what you're trying to do for a learning rate, because you know how if we have a, okay, let me go back. So if you know that if we have a, what's it called, a negative slope, then we need to increase. So using the slope, we can figure out the direction to update, like increase or decrease the parameter. But then we need to figure out how much to increase or decrease the parameter. Because let's say you're starting from the right dot and you increase, I mean, you decrease too much, then your new cost value might actually be bigger than your starting cost value. So what we need to do is use learning rate to figure out how much to update. So we already can figure out how, like the direction to update, but we don't know the how much to update, how much to increase or decrease. Does that make sense? Okay. So let me go. Okay, I think there's a. I think I know what happened. Okay, so what? So put a guess. Put an other guess, cause like you learned some stuff, I guess maybe. Or do you want to still stick with 0.4? Okay. So what you're saying is that you're gonna use 70% of the 70% of the derivative. Okay. So that's technically what you're saying. You're saying that you're gonna use 70% of the derivative to increase or decrease a parameter. Okay. So so over here, what happens is that you see the error, right? So what we have is runtime warning, overflow occurred in square. So if you go back to our cost function, if you go back to our cost function over here, what we do is we take the mean of the square of the differences. So if the difference between the prediction and the what's it called and the true value are really far away, then when you square them, you're gonna get a really huge number, and that's what overflow means. So that means your cost, since if this is too far away, if like these values are like really far away, that means your update um failed. So like your update, you increased it way too much so that you increased or decreased the parameters so much that you went all the way. So let's say you start from the right side, you went all the way to the left side and you climbed the hill of the left side. So that's what happened. So so are you gonna decrease or increase your learning rate if this happens? Yeah. Okay, so what new value? Okay. So this is saying that you're going to use 40% of your derivative. And then also, don't forget mu. Mu is the coefficient of friction. So if you have momentum, like, oh my God. So if you have momentum, your velocity on every update is going to change by your current velocity plus how much acceleration you add by your derivative. So let's run this. Increase or decrease learning rate. To what? Okay. So this time you're using 10% of your derivative for your acceleration. How about now? What do you think? Wait, what do you mean when too low? The learning rate is too low? Okay, so here, let me tell you something. So you remember this data set? You remember this data set? And okay, so this data set, what would be the bias value? What would be the optimal bias value for this data set? 20, yes. How about the weight? Okay, so if you look over here, we started with a weight really close to 0, and we started with a bias really close to 0. In the end, our weight has become this. And this is technically saying negative 2.33 times 10 to the 288. That's technically what the E plus 288 means. So what happened to your weight is that it's a really huge number right now. It's like, well, actually, no, because of the negative over here, it's a really, wait. Well, it's a really negative number. It's a really negative number. But your weight, what you want the weight to be is 10. You want the weight to be 10. And then if you look at your history of your weight, what happens is, okay, yeah, that's not helpful. Let's see the cost. Okay, you see the cost, it just explodes. It explodes because your weight went so huge that when you made your new predictions, they're off by way too much. So that means your learning rate is too high, okay? And also, if you look at this gives away if your learning rate is too high. Because if your cost is infinite, then that's a problem because, yeah, you don't want a lot of, like, you don't want infinite error. That means like your model is really, really dumb. Okay, so what's your new guess? Okay. Okay, so over here, your weight has become 10 and your bias has become 20. So now it works correctly. And then your cost has become really low because that E minus 5 is technically saying 8 times 10 to the negative 5. And that's a really small number.